Okay, we're going to combine two lessons into one. We'll just do the lesson today, and then tomorrow will be practice problems for all of these. Okay, so 11.5 and 11.6 are both actually similar. We're looking at similar figures, but we're going to compare area and volume and see how they are related. So let's actually start with a little warm-up here. We have two triangles. We're told they're similar. We are looking to find their areas. Okay, so first thing to notice here, if I compare, let's see, 18 to 36, this triangle's twice as big. I care about that because I will need the height of that triangle to find its area. Okay, so I do want you to notice that the scale factor here is 2 to 1. Okay, or if you were setting up a ratio, maybe 2 over 1 or 1 over 2, whichever one you chose to use. Any of these describes how those triangles are related. Okay, so let's find their areas then. So for the smaller one, triangle ARM, the area is 1/2 base times height, 1/2 times 18 times 14. We get 126 square centimeters. Now, it's tempting right now to say, okay, let's just double it, right? This triangle's twice as big, so shouldn't it have twice as much area? Well, let's find out. Triangle LEG, its area is 1/2 times 36 times 28. That's not twice as big. That's not 252, right? That would be what we would get if we were to double that. We actually get 504 square centimeters for this one. So maybe surprisingly, even though the triangle side lengths double, the areas do not. Okay, there's a different relationship here that we're looking for. And it actually, in this particular problem, this is not how they always will look, but this is times 4. Okay. Now, let's just do a quick little, like, what's going on here? Let's think about this. Because both of these measurements double, both base and height, let me write this area as this. 1/2 times, instead of 36, I'm going to write that as 2 times 18, and then 2 times 14. And you can see there are two 2's that show up in that new calculation, right? It's almost like we're doubling it twice, right? So what actually occurs here with area, we're just going to jump right to the conjecture. Pause if you need to write this out on your own. So if the corresponding side length, and it has in there, or radii, because this could work with circles as well, of two similar figures have this ratio, m to n. Now those would just be some numbers, right? Maybe 2 to 3 or 7 to 15, whatever they might be. Then their areas compare in, and I think this is not very surprising once you see it, m squared to n squared, right? So that kind of fits. Just think about how we measure area. We're always using square units. The ratio is also squared in there. That, by the way, is the same as this. If you want to think of this whole original ratio and just squaring the whole thing, these are equivalent to each other. But it goes back to that it shows up in here twice. So unfortunately, doubling something, the side lengths, makes this a little bit tricky to work with, but the 4 actually comes from 2 squared. All right, if we would have made the triangles 3 times bigger and the scale factor was 3 to 1, the areas would be 3 squared, or 9 times bigger. Okay, so it comes from, and we'll go through an example and see exactly how this plays out. Let's actually just do that now. Okay, so here's our first one. And copy down, pause what you need to do here, copy that down. So we have two similar triangles, CAT and MSE, nicely positioned, all facing the same way. They give us the area of CAT, so that's the bigger one. We're trying to find the area of MSE. Now notice we don't have a base and height really for either of them. So I'm not going to calculate the area using the area formula. I'm going to calculate the area using this relationship I know between their areas, how their areas compare to one another. Okay, so here's the first thing we need to figure out is how do the sides actually compare? So we kind of start this in the same way we would have any other problems, but I'm going to put off to the side here. There's two ratios I actually care about. So the sides have this ratio, 6 to 12. It's not a bad idea to reduce these just because when we square them, the numbers are a little more manageable. Okay, so the sides are in this ratio, 1 to 2, or 2 to 1 if you want to talk about the bigger one first. But I'm not doing anything with this to find the area of triangle MSE. The answer is not 36. Okay, let me put a big star here. It's not 36 square centimeters. That's what I think prior to today's lesson, that's probably what we would have just thrown in there. What we need to do is take our side ratio and square it. So that's 1 squared over 2 squared, or 1/4. So the ratio is actually 1 to 4. This is the one we care about. So when we're setting up our proportion, we need to make sure you're using the proper ratio. If I'm looking for an area, I need an area ratio. That is by far the easiest place to make a mistake in these problems. It's just to go with the side ratio and be done with it. Okay, so when I set up my proportion now, it actually looks like this. 1 to 4 equals, and then let's see, CAT again was the bigger one, so I'm going to put 72 on the bottom here. X would be my missing area that I'm looking for. Okay, so 4x equals 72, or x equals 18 square centimeters. Okay, make sure you are using the correct ratio. Okay, next one here. Number 2, they tell us that the rectangles are similar, and the area of RECT over the area of ANGL. So the ratio of the areas is 9 to 16. Now, this is just the ratio. This doesn't necessarily mean those are the actual areas. Okay, they're just that ratio they set up, they reduced all the way. In fact, so look at ANGL. If one of the sides is already 24, there's no way its area is just 16. So this is reduced already for us, okay? So we're kind of working backwards now. So this time they tell us how the areas compare to one another. We are looking for the length of this side. So this is the x in this case. So we've got two ratios here. I'm just going to rewrite this. So the areas have this ratio, 9 to 16. We just need to go backwards now since we're looking for a side ratio. Think about how we would do that. If we were going from side to area, we square it. If we're going to go in reverse, do you know what that would look like? We're just going to take a square root of both of these. So 3 to 4 is the ratio that we'll work with. So this is the one that you should be using in your proportion. If you're looking for sides, make sure you have a side ratio. So 3 over 4 equals, let's see, smaller one on top, x over 24. Okay, we end up getting 18 for that one also, actually. We'll just call it centimeters. Okay, so just make sure you have the correct ratio before you start. Now, similarly, let's jump right into volume here. There's a new ratio that we need for volume, but I bet you could guess it if I asked you to. So if the corresponding edge length, so they're like, if they're talking about a cube, they don't call that whole thing the side, they call it the edge, right? A cube, like this little piece is the edge here. You get the idea. Okay, so, or radii or heights, any of those one-dimensional measurements. If their ratio is m to n, their volumes have this ratio, m cubed to n cubed, which is the same as taking that original ratio and cubing the whole thing. Those are equivalent to one another. Okay, so the nice thing about this, it works, very nicely with what we know about area and volume so far as their units go. So hopefully we're not getting the area and volume squared versus cubed mixed up in these problems. You just need to know which one you're working with. Okay, so here's the next one. Number 3, we have two similar pentagonal pyramids. Now look what they're giving you. H over H, that ratio is 4 over 7. That's a one-dimensional measurement. So this is kind of the equivalent of the side ratio. Those are not technically called sides, but we'll have like three baskets we lump these in. We've either got the side ratio, the area ratio, or the volume ratio. So our side ratio is 4 to 7. Our volume ratio then, we're going to take 4 cubed over 7 cubed. Don't be alarmed, we're getting some pretty big numbers here. 64 over 343. That is the ratio that we'll use in our proportion to find a missing volume. Okay, so once you do the work to find the ratio, it's just like all the other problems. Set up a proportion, 64 over 343. The small one is 320, so that's going to go on top. The bigger one is the one I'm looking for. We'll just call that x. After you cross multiply and solve for x, we get 1,715 cubic centimeters. Okay, so just make sure you have the correct ratio to start. Okay, one more little practice problem here with you. The volume of the, large cylinder is 64, the volume of the small cylinder is 8. Okay, they give us one of the smaller radii. We're looking for the larger one, R. So this, again, we're sort of working backwards here. So we're going to start with the volume ratio. So this is kind of one of 3 buckets, right? We've got the sides, the areas, the volume. So we have the volume ratio, 64 to 8. You certainly could flip that around as well if you'd like. What we want is the equivalent of the side ratio. So radii in this case, or even if it was height, or for that matter, circumference, those all fall into the side bucket. Those are all one-dimensional measurements. So to go backwards here, so let me flip back to the last problem real quick. So to go from side to volume, we cube that. Now we're going in the opposite direction. So we're going to take the cubed root of those. So if you're comfortable doing that in your calculator, you could take the cube root of 64. Let me write it this way. Over the cube root of 8. You certainly could get numbers for those. I might suggest doing this. If possible, reduce it. Just makes it, again, a little more manageable. This volume ratio is the same as 8 to 1. So this one is 8 times, or it holds 8 times more stuff, if you want to think of it that way. So I could also find, let me kind of separate this here, the cube root of 8 over the cube root of 1. So we're thinking of what number multiplied by itself 3 times gives me 8. That would be 2. 2 times 2 times 2. And then this one, I like reducing it because the cube root of 1 is just 1. Okay, you could certainly do this one. We would get, let me squish it in here, 4 over 2, but that's the same as 2 to 1. Either one of these that you decide to work with can get you the right answer. No big deal. I'm going to stick with this one. Okay. So when I set up my proportion now with my missing radius, I want 2 over 1 equals, here's my bigger one, we'll just call it capital R, over 10. Okay, so you can see the radii are, let's see, what, 10 times bigger in this case. So this should be, excuse me, I phrased that wrong. From one ratio to the next is times 10. So R is going to be 20 centimeters. But you, of course, could just cross multiply and solve. You'll get 20 right away anyways. Okay, please make sure if you need to go back and copy anything down, make a better diagram in your notes, that you do that. Tomorrow we will do some practice problems using proportions and area and volume. Okay, have a great day.